Have you ever pondered why time only seems to move in one direction, from the past towards the future? This is a question that has baffled humanity for centuries, sparking countless debates among philosophers, scientists, and thinkers alike. Time, in its essence, is a fundamental part of our existence, a constant thread woven into the very fabric of our lives. Think about it. Every moment of our lives is governed by time. From the ticking of the clock to the changing of the seasons, time is always marching forward, never backward. It's a universal phenomenon, an unbroken, continuous flow that guides us from the cradle to the grave. This linear, one-directional perception of time is so deeply ingrained in our consciousness that we rarely stop to question it. But today, we're going to do just that. We're going to explore the concept of the arrow of time, a term coined by British astronomer Arthur Eddington in 1927 to describe this forward motion of time. This arrow, it seems, always points from the past, through the present and into the future. But why is that? Why does time appear to have a preferred direction? Why can we remember the past, but not the future? Why are we always moving forward in time and never backward? These are the mysteries of the arrow of time, questions that have puzzled scientists for decades. They've proposed many theories, from the laws of thermodynamics to the principles of quantum mechanics, in an attempt to unravel these enigmas. Yet, despite all the advancements in science, the arrow of time remains one of the most profound mysteries of our universe. It's a concept that challenges our understanding of reality, compelling us to question the very nature of time itself. So if time is a fundamental aspect of our universe, why does it seem to have a preferred direction? Let's dive into the theories that try to answer this question. The arrow of time is a concept that's been puzzling scientists for decades. What exactly is it? Well, in simple terms, the arrow of time refers to the one-way direction or asymmetry of time, which moves from past to future. Have you ever wondered why we remember the past but not the future, or why we can't unscramble an egg? These questions hint at the underlying nature of time's arrow. Now, this arrow isn't a physical entity that you can touch or see. Rather, it's a metaphorical representation of time's perceived directionality. It's the reason we feel the flow of time, the relentless march from the past, through the present, and into the future. To delve deeper, scientists have identified three main types of arrows of time: thermodynamic, cosmological, and quantum mechanical. The thermodynamic arrow of time is based on the second law of thermodynamics, which states that systems tend towards disorder or entropy. This is why your coffee cools down, and it's why we age. The cosmological arrow of time, on the other hand, relates to the expansion of the universe. Just as a film of the universe played backwards would show contraction, the real universe expands, providing a directionality to time. Finally, the quantum mechanical arrow of time is the most elusive. It suggests that at the quantum level, there may be processes that are not time reversible, offering a possible explanation for the arrow of time. But this is still a controversial and heavily debated topic. So, there you have it. The arrow of time isn't an arrow at all, but rather a way to conceptualize the forward flow of time that we all experience. It's a fundamental aspect of our existence, and yet, it remains one of the greatest mysteries of our universe. Now that we have a basic understanding of the arrow of time, let's delve into the theories that attempt to explain this phenomenon. The thermodynamic arrow of time is based on the second law of thermodynamics. But what does this law say? Well, to put it simply, the second law of thermodynamics states that the total entropy or disorder in an isolated system can only increase over time. Picture a room full of air molecules. If you could see each molecule, you'd notice they're not all neatly lined up. Instead, they're bouncing around haphazardly, creating a state of disorder. This is entropy. Now, let's say we introduce a sweet-smelling perfume into the room. At first, the perfume molecules are concentrated in one area, but soon they start to mix with the air molecules. The more they mix, the more the disorder or entropy increases. Eventually, the perfume molecules spread throughout the entire room, reaching a state of maximum disorder. This is the second law of thermodynamics in action. So, how does this relate to the thermodynamic arrow of time? Well, if time were to run backwards, the perfume molecules would have to unmix and return to their original ordered state. But that's not something we observe in nature. The perfume never unmixes, the egg never unscrambles, the ice never unmelts. Time, it seems, has a preferred direction, from order to disorder, from past to future. This is what we call the thermodynamic arrow of time. It's the idea that time flows in the direction of increasing entropy. It's why we remember yesterday but not tomorrow, why we grow old but never young. It's the reason time seems to flow in one direction. But here's the catch. The second law of thermodynamics is a statistical law. It's based on probabilities. It's overwhelmingly likely that things will move from order to disorder, but it's not guaranteed. There's a tiny chance that the perfume could unmix, the egg could unscramble, the ice could unmelt. But these events are so incredibly unlikely that we don't observe them in our everyday lives. So, the second law of thermodynamics gives us one explanation for the arrow of time. But there are other theories as well. Beyond thermodynamics, cosmology and quantum mechanics also offer explanations for the arrow of time. Let's first consider the cosmological arrow of time. This is based on the observation that our universe is expanding. Picture a movie of the universe playing in reverse. You'd see galaxies converging, not diverging, which seems highly unnatural. This suggests an inherent directionality to time, one that moves from the Big Bang towards the endless expansion of the universe. But what about at the tiniest scales? That's where quantum mechanics enters the picture with its own arrow of time. Quantum mechanics, the bizarre and often mind-bending realm of the ultra-small, deals with particles like electrons and photons. Here we encounter a concept called quantum entanglement, a phenomenon where particles become intertwined, their states instantly affecting each other, no matter the distance. But where does time come in? Well, some physicists propose that the process of entanglement between particles could give rise to an arrow of time. The idea is that in the early universe, particles were highly entangled, but as time progressed, this entanglement has become more dilute. This suggests a directionality to time, going from a state of high entanglement towards one of lower entanglement. Of course, these are just theories. The cosmological and quantum mechanical arrows of time are still subjects of ongoing research, and there's much we don't yet understand. But they're part of a broader effort to unravel one of the greatest mysteries in science. Why does time seem to move in one direction from past to future? Perhaps one day, we'll find a unified theory of time that brings together thermodynamics, cosmology, and quantum mechanics. Until then, we'll keep exploring, keep questioning, and keep pushing the boundaries of our understanding. These theories, while complex, offer fascinating insights into the nature of time and its directionality. So why does time flow in one direction? The answer, it seems, is still shrouded in mystery. As we've traversed the labyrinth of time's enigma together, we've touched upon the fascinating theories that scientists have put forth. From the arrow of time to the thermodynamic, cosmological, and quantum mechanical aspects, each theory offers a unique perspective, yet none provide a complete answer. The arrow of time, that metaphorical pointer guiding us from the past to the future, is a compelling concept. It suggests that time is asymmetrical, flowing like a river from the past towards the future, never the opposite. Yet, the mechanics that facilitate this one-way journey remain elusive. The thermodynamic arrow of time brings us face to face with the second law of thermodynamics, proposing that time's direction is intertwined with the increase in entropy, the measure of disorder in a system. As the universe tends towards chaos, so does time march forward. But this still leaves us with unanswered questions about the initial low-entropy state of the universe. The cosmological arrow of time, on the other hand, draws upon the expansion of the universe. As galaxies drift apart, time too, it is suggested, drifts forward. Yet this theory too does not fully explain why we can't travel back in time. The quantum mechanical arrow of time, perhaps the most abstract of these theories, posits that time's direction may be tied to the asymmetry at the quantum level. It's a theory that's both intriguing and mind-boggling, yet it's still in its infancy and far from providing a comprehensive explanation. All these theories, while fascinating, remind us of the complexity of our universe and the ongoing nature of scientific discovery. They invite us to think, to question, to wonder. The mysteries of time are far from solved, but isn't that the beauty of science? The chase, the exploration, the thirst for knowledge that keeps us asking, why? While we may not have definitive answers, the quest to understand the arrow of time continues to drive scientific exploration, inviting us all to ponder the fascinating mysteries of our universe.